All right, thanks, Christoph. It's my pleasure to be here today. Please ask questions. It's a lot more interesting to me if you ask questions and uh, make this a little bit more interactive. So my talk is a bit of hardware insecurity. It's actually going to be a little bit more than a bit. It'll be bite. So that's my dad. Do you have dad jokes here? Yes, that's my dad joke. Okay, and that is my dad. There will be a lot of them, but that is my first dad joke that we have. So let's get started. So I've done a lot of work. I'm not really a good formal mathematical person, to be totally honest, but I've started doing a lot of more work in verification, so security verification. And it's kind of give you a notion of the history of verification, for instance, at least in my eyes. So a lot of times, especially in hardware, we think about this in terms of how do we verify something or how do we make sure that hardware is secure? And a lot of times we just do this by obscurity. So hardware is in some sense hard to reverse engineer. It's getting a lot easier, as Christoph, a lot of people in this group know, right? It's a lot easier now to sort of reverse engineer it. But at least in the past, it was a lot harder. And it's a lot harder than, say, software kind of stuff. So a lot of industry, for instance, has relied on the fact that we can just do this security by obscurity, right? That's never a good thing. There's also sort of the intimidation, and maybe that's the Christoph's thing. So, if you go and reverse engineer these things, some of these companies get really pissed off at you, right? And they say these sort of things. They say, we're never going to fund Christoph, and we're never going to fund anybody else in FPGA security ever, right? For quite some time. And so that is the sort of the proof by intimidation, right? So don't mess with us, because if we do, then you're gonna be in trouble, right? And then there's a lot of hand waving. This is a good professorial type of thing. Oh, trust me, it's sort of secure. And then this, I think, honestly, is kind of the thing is that we have, in terms of designing hardware, right? We have pretty hard deadlines, right? Strict deadlines, especially in industry, right? We have to get these chips out. We have a deadline in which we have to get them out. We have to make sure that they just work. It's hard enough in hardware to make sure that it's just functionally correct, right? And that's where we spend the majority of our time in developing chips, semiconductors. And then also to think about whether or not they're secure, right? And the great thing about hardware security, in my opinion, is that it will never be secure. So we have good job security as a hardware security people, right? And so the last one, and I kid you not, so this was something many years ago at Host. Host was one of not the best conference. Chess is the best conference in hardware security, but maybe the second or third best conference in hardware security. I asked a very big German professor in hardware security. I said, how, no one here. So, but a little bit south of here. I'll give you a hint where that person might be. They had developed a processor or hardware, and I asked a very serious question. I said, how can we trust that your hardware is secure? How should I trust you? And this person said, well, that's a very religious question. So he was citing, like, and it's like, oh, I'm really not trying to like attack you, right? Like saying like you're a bad person or anything, but I was seriously asking a question, like, what did you do in order to look at this piece of hardware to tell us that is actually secure? And oh, that's a very religious question, Ryan. So they were citing a proof by a higher deity. So how do we do that, right? So that's what I've been working on for quite some time now. And so one thing that we often do in terms of in hardware is we think about functional verification, which has been around since the early days of hardware, not security. We think about writing assertions, right? And this was going back to the days of Alan Turing. Whenever this was 70, 80 years ago, probably, saying we have to write assertions and write a set of assertions in order to make sure that this thing is correct. And I think the same is true for hardware. If we can write a set of assertions to start thinking about how this is secure. Right? So I'm not the first person to say this sort of thing. There's a number of, actually, I think a bunch of German people that are doing this sort of stuff, is saying we should write these assertions or these tests, and we should sort of iteratively do this, right? All the way to Wolfgang. I think Wolfgang was here not too long ago, pretty close as well. Talking about writing properties, right? Writing these properties, we do this, and if we can continue to sort of iterate writing these properties, these security, these safety, these functional properties, then we have a hope at it being more secure. Again, it won't ever be 100% secure, but we at least will make it more secure, so that when it gets attacked, and if you're a company, it gets attacked, and you come back and your customer said, what did you do? And you can say, look, here's all these things that I did. I met the standard, the state of the art in terms of security. I proved this and that. So that's what we've been pushing. And we have this sort of 6-step thing. A number of people have talked about these sort of steps. They call them different things, but I think these 6 steps pretty much articulate the types of things that you want to do when you're thinking about, here's my, and a lot of the security that we do is pre-silicon. So here's my hardware design. And a lot of times when you start doing security, unfortunately, the hardware design is fairly fixed a lot of times. They're starting to think about security a little bit earlier in the game, but these days it's kind of near the end. You have to go through these different steps. So let me go through these process of steps. Randall Munroe, you're probably familiar with XKCD, and wrote this comic some time ago, many years ago. And so this is the modern tech step, right? So we have this compromised by customers and former employee, back when Bitcoin was important, compromised by unknown hackers, compromised by our government, foreign government, and then we have this hardware vulnerability. So hardware security verification, or hardware security is a big deal. We were in XKCD some time ago. And so, the mouse over for this, they always have these mouse overs where you sit that and this comes out. So you got to feel bad for those nation state hackers who spent years implanting and cultivating some hardware exploit, only to discover the target database has already been exposed to anybody with a web browser, right? And this is true. Like a lot of times the stuff sits way up here, right? We just don't think, someone doesn't think about security way up here. And, all these NSA type people, Mossad type people, right? I don't know what the German equivalent to this is, but I'm sure you have one, are down here like trying to do these exploits, but then we just have these idiots that are doing these bad things, right? So James Mickens, if you don't know James Mickens, you should know James Mickens because he is an amazing speaker and amazing security person as well, and very funny. So I encourage you to watch some of his, much more entertaining than my talks for sure. So he wrote this article more than a decade ago talking about threat models. And he said, okay, you have different types of threat models, right? So if you're trying to avoid, your girlfriend or boyfriend breaking into an email account, looking into some things, you should just make stronger passwords, right? If you're trying to avoid organized criminals to do that, stronger passwords plus some common sense, right? If you're trying to avoid the Mossad from breaking into your account, there's nothing you can do, right? Mossad is going to do things, right? They're going to do those things, right? And so more to the point, like this is defining your threat model. This is really important, right? In my opinion, probably the most important thing, the highest level thing is you have to talk about what you care about and what you don't care about. And maybe a good thing or a bad thing, we do this really well in security papers, right? So if you, a decade ago, before I was a security person, I was writing papers and they were all getting rejected into these security conferences. And a big thing that I learned is I have to have a section on threat models, right? You have to have that because that's where you say, here's what I care about and here's what I don't care about, right? And that's important. And I think that's important in general, right? You have to say, I care about power side channels. I don't care about power side channels. I care about microarchitectural text. I don't care about microarchitecture, right? I care about strong encryption, whatever, right? These are the things that I care about, right? You have to say this, right? This is the type of thing. And we do this to the extreme, I would say now, is like I see these papers all the time. It's like, here's my threat model, and it's going to be very specific, and I'm going to carve out this tiny little niche where I'm perfectly going to fit into. But we're going to save the world until our next paper, right? That's what happens. But it is important, I think. So that's the threat model. That's really high level, right? You have to say at the high level, what do you care about? What don't you care about? What do customers care about? What do customers don't care about? Then once you have that, you have to start moving down. And ideally, we're going to try to get down to these formal properties. So what I'm going to do is I'm going to walk through a study that we did a few years ago with Jason was my former PhD student, now the CTO of a company called Insecurity, which develops hardware security verification tools. Dom was at Google doing OpenTitan and now spun out a company called Zero Risk that just got a good amount, $10 million funding to do some stuff. And so, Dom cares about OpenTitan. So if you're not familiar with OpenTitan, it's an open source hardware root of trust developed, managed by Low Risk, Cambridge company. but totally open source, right? So Google paid a lot of money to do this, and then Google, when Google was firing a lot of people, fired the whole team. And then Dom took the whole team and made us stuff. It's pretty good, pretty smart. That Dom guy is pretty. So anyway, back when Dom was at Google, we said, let's do this verification thing. And so the first thing that we did is we said, okay, we care about, Dom told us, because Dom built this, right? So Dom said, we care about this thing called the one-time programmable memory. This is where we store all of our secrets. Okay, it's a one-time programmable memory, usually like a fuse-based memory where you put stuff into, and we care about that. And then it has a sort of a wrapper around it that allows you to access it and does access control and all kinds of different things. Okay, so let's focus on that. And let's focus in particular on this asset, which is called the RAND constant key, RAND constant key. Basically, this is a key encryption key. So we use this. This is usually burned into the hardware. Not even fuse-based, but literally sort of programmed into the hardware. Zeros and ones connected to VDD and ground. Changed, hopefully, by every vendor to be something a little bit different. But this is used in this scrambler, a present scrambler, which you guys are all familiar with, very sort of fast crypto core that will then encrypt all of the stuff in here, right? Yeah, this is a present, yeah? Familiar with that? Yeah, yeah, it's amazing, yeah. The only on the yeah. So yeah, there it is. So that key here is really important to protect because if you can get access to this, you can get access to all this kind of stuff. They assume that anybody can look at this through reverse engineering, sand and scan sort of stuff. And so they encrypt everything that goes into here with this key that is supposed to be very secure. So it's an important thing. So that's our asset, right? That's identify asset, right? That's our identify asset. And then we have to start moving into properties. Okay, so as we start moving into properties, we start asking these sort of questions. So, where does this information go? Where does this information about this key, where can it possibly go in my chip, right? Can it get outside of this sort of boundary? That would be a question. How does that go, right? When does it go? Why does it go? And if it does flow, it does move into places that we don't, how do we stop it, right? So those are the sort of questions. So we have this requirement. And usually these requirements are English language, German language, right? Some language requirements, so not formal in any sense. But you write these down. You say the RAND constant key should not leak outside of this wrapper, right? This OTP memory controller. And then that is the security property. So then you can formalize this, right? So this is a property written in Insecurity's flow language. But there are a number of other tools that have similar types of things where you can write a property like this. So let me step through this. So you say this asset, this key, and it's actually called a couple of things here, but that's basically that key, should not flow, should not leak, right? So this is a confidentiality statement to all of the outputs, any output of the OTP controller. Okay, so that's the formal way of doing that. And then we can take that and then we can start to see through some verification tools whether or not this actually happens. So we formally specified it. Now we have a bunch of tools that have come in the past decade or so that allows us to analyze whether or not this property, this hardware, this piece of hardware, adheres to this property. Okay. One way that we do this is through formal tools. Functional hardware verification is one of the places that a lot of formal methods people say, like, look, we've actually done some good work, right? We've done some work that is used in practice a lot, right? So formal in hardware verification, functional hardware verification is quite strong. So you take that hardware design, you take that security property, you take some different types of formal solvers, both commercial or academic, and then you can say, does this hardware, this design meet this property, yes or no? So formal is amazing when you can do it, but it doesn't scale often. So that's the downside of formal. And so the next step then is if your design gets a little bit bigger, you say, let's do something in simulation or even bigger in emulation, right? So there are also tools, commercial and academic tools that will say, take the same thing, take this property, take this hardware design, take a test bench. I should have added a test bench in here. So just a normal test bench, functional test bench, nothing special, and then track it, right? So we're saying here, is we're saying this starts as tainted. This starts as information that I want to track. And then here's a bunch of other things. And this is actually an output. And you can see when these turn red, basically means that information has about this thing. And these are, the way that this is done is there's actually 3 different keys that you can cycle through in the OTP. But so we mark all of those as tainted always. And we want to see where information about that goes to different places in the design. So you can see it at some point we're at some way down the test bench. This output of the scrambler has information about this. It becomes tainted. That's not surprising, right? The output of your crypto core should contain information about your key. It has to, right? And then also it goes at some point to this output token, which is bad. So that means that potentially bad. It's potentially bad. That means that this information from your key has gone to one of the outputs of the OTP at this time. Okay, so that's what the verification simulation IFT information flow tracking does. Okay, so let me now sort of talk and step through a few of these other ideas with an example of a recent work that we did with Wolfgang's group that was just presented last week or 2 weeks ago at DAC. So what Wolfgang does is his group has developed this UPEC tool, which is a formal tool, 2 safety tool. So basically take 2 hardware designs, and then you constrain some of the inputs to be the same, and then you see if any of the outputs become different, right? It's basically a way of doing information flow tracking formally. And they specifically have a version of this tool that looks at data obliviousness, which is timing channels. So timing channels, okay? So they're looking for timing channels in hardware designs. So we've been working in a sort of a group at Intel, a research project, bigger research program at Intel on scalable assurance. And over the past few years, we've been sort of seeing Wolfgang's work. And at some point, a couple of years ago, a year ago maybe, my student Andy and Lucas, one of Wolfgang's students, got together and said, hey, I think we can help you, right, to make this better. Because this actually turns out to be kind of hard to do. And I'll step through why this is kind of hard to do. It takes very smart people like Lucas to do this. It's not easy. It takes a formal person that understands things. So here's what FastPath does. Okay, so it takes your security specification. So that's your property. Takes your RTL, your hardware design. And what it does first is it does something very simple. It just basically does a structural analysis on the hardware design. And it says, can this asset, can this random constant key, can it possibly go to any of the outputs? Is there a path, a set of nets, a set of wires from this to the outputs? Okay, does that exist? That's very easy to do, and that's very fast to do, right? That's not precise, but it's very easy and very fast to do. And so if it doesn't exist, if there is not a path from the key to those outputs, then you can say with 100% assurance that it will not flow. It's impossible, right? And we're not talking about power side channels and things like that. We're talking about actual information flowing through wires, right? It's functional values, right? However, if it says there is a path, you can't say anything about that. If there's a path, that path may not be realizable. That path may have a bunch of conditions on it that can never happen, right? But if it says there's no path, we can stop, okay? So that's the first thing. So that's sort of the first step. It's a very simple analysis. It scales like that. Every hardware design, you have to parse it like this. And so that scales very quickly. Okay, so now if that fails, if there is a path, we have to do a deeper analysis. And so the first thing that we do is we run one of these simulations. And we say, with a very simple random test bench that we just cooked up, it's nothing fancy, right? Or you can use functional test bench if your design has it, but we just used random test benches, very simple ones. Taint this input, run some random simulations for a number of cycles, not that many cycles, and see, does it flow to these outputs, right? Because this random simulation may force this information to actually happen. And if it does flow, then we know that there is a flow, right? If it doesn't flow, we're back at the same point kind of as before. There might be a flow. It may be just our test bench isn't good enough, okay? And so that's when we then go to, so a couple things here. If there is a flow, right? We know that there's a problem. One second. And then that might be a problem with our design, or that might be our property not being specified very well. Okay, so there might be two things here, but we know we have to fix it. We either have to change our design, or, and this happens all the time, we write a property, and that property that I wrote was actually wrong, and you'll see why in a second, that it's not correct. You think it's correct, but it's not correct, and you get a counterexample, and you're like, oh, actually, this is okay. Okay, question.
So, thank you. My question, these information flow tracking tools, these, as far as I know, usually already do this structural analysis, don't they? And as far as I understood, in your structural analysis, you're in a sense just ruling out paths where there is no, like, when there is no connection, you're not analyzing it. And then all connections which exist, you're just forwarding to an information flow.
If they're formal, they may not. Like, so UPEC did not, for instance. So UPEC is the academic tool. It did not do the structural analysis. You would think they would do it. You would think they should do it. I agree. That would be an easy way. But I think a lot of them just fall back, especially the formal ones, just fall back on whatever their formal solvers are. Now that underlying formal solver will look first for a structural thing, which is probably a good idea, like I think what you're implying, then yeah. But the IFT tools, and I know this for certain because that Insecurity company, I co-founded that company, and I don't know everything that's going on anymore, but they don't look for structural stuff at first. They just run the simulations at first before running anything. So, so it depends on the. Yeah. Thanks. Okay, so now if we don't have a counterexample, so basically there was no flow, then we don't know if it's secure. So that's when we have to go into formal. Okay, because we basically said, let's try, do a best effort. Is it connected? No. Let's run the simulation. Does the simulation exploit this flaw? No. Okay, we have more confidence that there's not a flow, that it's secure, but we don't have total confidence, and that's where you want to use formal tools. So that's when we use the UPEC tool. In fact, we can take some shortcuts on this tool. So what this tool does is basically says, I'm looking for, from my inputs, do any of my inputs affect control state? Because if any of my data inputs, if they affect control state, then through some proofs that are in their paper, you can know that that is going to cause a timing channel. Okay, if it does not affect control state, any of my data inputs do not affect control state, then I know I can't have a timing channel. That's sort of the contrapositive to that. Okay, so they start with this thing, and then sometimes flows will happen, and they'll say, because they don't specify the property well, because it's hard to do that. So they start off and they say, none of my where's this property here? It is here. None of my data inputs should flow to control outputs. Okay, and that's what it's saying. That's the property they're trying to prove. And so they just do that very simply. Now, what tends to happen a lot is that they'll do this, and there will be a flow, and they'll look at that flow and they'll say, actually, this is okay, because this is a control signal, but this is a control signal for like a buffer. A data buffer is a good example. And that is okay. That's an okay thing. But that requires Lucas to look at that counterexample and say, that's actually okay, let me refine my property. Okay? And the sort of the dirty little secret that we learned from them is that happens a lot. Okay? That happens a lot. And that's not an uncommon thing. That's common for most formal tools, right? You write a property, the formal tool says, oh, I got you. I found this thing. And you're like, it's actually okay, formal tools. And you basically make an invariant on your property. You change your property to modify it. But because we know some things, we can sort of specify this initially. We can say, some of these things might be okay. Some of these things might not be okay. And we can sort of precede, because this tool uses symbolic analysis to precede some of their properties that are invariant. Yuval, your question.
Yes, my question is, how often does it happen that the human in the loop is wrong and he says, yes, this is okay, but it's not really okay?
I have some numbers in a second, I'll tell you. Yeah, thanks. Okay, so that's that. Basically what we do is we kind of precede it. We use the tool. So we found some flows. We use the tool to say, are there any more flows? And so now we can already say these flows exist. We look at them and say these flows are okay. So Lucas looked at them already, and we found those already. So now we don't have to do this iterative, as much of this iterative thing. And then we say, are there any more flows that we missed? Okay, yes or no. And then we use that tool again to sort of, as it was before, to sort of finalize everything. Okay, and then if there's no exception here, we are 100% sure that this is secure, okay, because we went through a formal analysis. So here's the result that you're sort of asking about. So a number of designs here, you're probably familiar with them, starting from some sort of fairly simple crypto cores to more complex processors. You can see the state size. Some of these designs, these simple ones, the structural analysis just finds that there's no flow, there's no connections. So you don't need to do anything, okay? But originally, so this is the original paper, Yuval, I had to do this iteration 33 times on this fairly simple design. 33 iterations. Sometimes they talk about how much time it took, sometimes weeks to months it took them. It took Lucas weeks to months to do this sort of stuff. Where it wasn't even connected, right? It wasn't even connected, right? They should have done this structural analysis like you were saying, right? And then there is a case here where the information flow tracking found that there's a flow. Okay, so the structural analysis said there's a connection, but then, so we don't know. So we went to the second step and we said, oh, we found it with our simple random test bench, okay? And then a bunch of these things then required us to go to this third step. But if you look here, you can see, here's how many times, look at this, 185 iterations that they had to go through for Boom. Boom is fairly complex, right? I don't remember how many stage processor it is, but it's an out of order, I don't know, tends to have 10 stage, I don't remember, but some fairly complex processor. 185 Lucas iterations on this thing, right? To make sure that that property is refined. And then we were basically able to get rid of a lot of those by doing this information flow tracking analysis, okay? So we didn't put time there because I think that's sort of arbitrary in some sense. And it was impossible because now Lucas already knew what everything was. So we would, hopefully he remembered it, right? And so, but these manual inspections are, I think, a good notion of how much effort that it takes. Okay, so having been in this Intel Scalable Assurance program for several years, going to these workshops, usually every year, the inevitable question that I always ask at this workshop or at a talk for formal, especially for formal, does your technique scale? And what they're really saying is, I don't think your technique scales whenever they ask that. And then what the people say is, yes, it scales. Look at it. We've done it on these open source designs, right? And this gives me to sort of one thing that I want to sort of make a bigger point at, and this is more maybe an industrial point than an academic point, but how do we know if we don't have the benchmarks, right? So we work with Intel, and they always say, oh, I don't know, Ryan, if your technique's going to work on our designs internally, right? Because our designs are much more complicated than your simple toy examples that you do in academic, right? But how are we supposed to know? How are we supposed to know as academics if we don't have access to these sort of things? So we really need bigger things, right? And we're starting to get them, right? Especially in the microprocessor space with RISC-V. There's a number of really good hardware root of trust open source ones. OpenTitan started that. Calyptra is now one that a lot of people are supporting, looking at cloud-based kinds of things. So I know very well. There's some nice network on chip things where you can make big, larger scalable designs from Columbia and Luca Benini's group in Zurich. And then some larger SoCs that, like Luca's group, tends to spit out these SoCs, kind of monthly. His massive group of seems like thousands of students that he has down there. But Carfield's a really great example. They're building an SoC that goes into cars. And so it's a fairly complex SoC that's in the open source. But we need more. We need more, right? If we're going to just say these sort of things. So here's a massive list from this survey paper that my poor former postdoc found all of these things and made a really nice slide of all of these different types of tools that do hardware information flow tracking. And so my big point here is, do we need more tools? Maybe. Do we desperately need more? No. I think this space is pretty good, in my opinion. There's commercial tools, there's good academic tools. Can there be more innovation? Of course, but we're pretty good here. Okay, so So let me stop. So we went here, went through this whole process with you on an example. And I talked a little bit about a technique to sort of make these verification tools work well, in my opinion. Sort of the three classes of those: the structural analysis-based things, the test bench based tools, simulation-based tools, and then the formal tools. Okay, those are the sort of three classes. And I'd say these are we're pretty okay. We've done a nice, good amount of research. We're pretty good. We can use these. We get up to here, and this is hard, right? This is Sisyphus pushing his poor rock up that hill, forever and ever, right? This is a lot of manual labor that we need to do in order to create these things. And these are teams, sometimes big, sometimes small, at companies. Intel has a bigger team that looks at this. AMD has a smaller team that looks at this. Qualcomm has an even smaller team that looks at this, right? So these are teams that look at these things and sort of manually go through this process and try to make their hardware secure. So how do we automate that, basically? That's what we've been looking at a lot more generally in the past 5 years in my research group and collaborators. So one way that we've done this is through a tool called Isadora. So this is with Cynthia Sturton at UNC, University of North Carolina. Cynthia was I don't know if you know Cynthia, but she is a ballerina. She was a former professional ballerina. And Isadora is a very tragic story in the ballet world. But she names a lot of her projects after ballerinas. And so this is the project Isadora. And so what we were trying to do that with her amazing PhD student, Calvin, who's now a professor at Willamette University, was automate the security property generation. And the way that we did this is we took our traces, run simulations, and take taint different types of things. So just taint different assets that we think are important, and then run simulations. A lot of times these are simulations that are given to us. So if you look at OpenTitan, for instance, it has hundreds of simulations that you can run that are smoke tests and initialization procedures, things like that. So a lot of times it's those, or you can do random things. So we take these, we get a bunch of traces, and then we have an automated way to turn those traces into invariants. That's what Isadora is at the big picture. So the first steps is that we look at analyze the flow relations. And then we look to mine in these invariants based on these flow relations. Okay, so the flow relations are, I don't want to get too deep into this, but basically this red is another signal. So every signal has a separate binary signal called its taint, often called its taint or its label, security label. And that red is a label for this signal. So is it set or is it not set? Red or not, or white, right? That's that signal. And so underlying a lot of the tools is that sort of notion of every signal carries an additional bit that you can mark and that will then automatically get updated depending on how the design is executing, okay? So that's what's happening. And then we can mine that. So we can basically say, okay, we have these traces and we have a bunch of tools. One of the sort of oldest one is called DICON. It's a tool not even for hardware, but for software that was developed at UW by Mike Ernst, I believe, to find invariants in traces. So we use that tool DICON, and then we can start thinking, wow, here's all these invariants. So invariant is something that holds across a set of time over time, right, or a subset of time. And it turns out you get a lot of these because these things are big, and then you have to filter them out smartly. And so that's the process of DICON. One of the things that you could get is you could say, well, perhaps an invariant is this. When this is set, this output, this data out, that's the output of your presence. That's the output of your cipher, right? That's the output of present. That key, that output is a function of that key, but only when ready out is set. And that's actually important, right? Because if before I wrote this property here. I just wrote this should not flow to, I said actually output, okay? But really what I want to say is this should not flow to any output, not just data out, but any output, but this is okay. Okay. When this is set, that flow is okay, because what does that mean? That means key is here, information about key is here, but if you all did your work well, that's mathematically secure, right? That is secure because the crypto engine says that that key is properly mixed, okay? But if it's coming out early, as actually in OpenTitan, this was coming out early. That was intermediate state, that was bad. So we found a flaw in OpenTitan where it was just spitting out, present was, I don't know, 9 rounds or something like that. And it was spitting out to the output internal state, which is not good, right? That's a very easy way to figure out your key. Okay, so what you needed to do, our fix was simple. We say our internal state should be, set that to 0 until it's really mixed, until it's properly mixed, right? But this invariant is something like that, and you can look at it and you say, okay, this is something that we need, is a good thing, right? That's what we need. And just more generally speaking, I don't want to spend too much time on this because it's pretty complicated, but big picture is we did a lot of access control work, being access control, sort of memory access control on IP cores. We built an access control mechanism that's in hardware that looks sort of like this. And we ran it through Isadora, and we were able to sort of see when flows happen between different parts of this. And so it was just basically, we call them insights. So they're not necessarily properties, but they give you some hints about when flows are happening and under what conditions flows are happening. So you can look at them and you'd be like, oh, this flow is happening, and it's happening a lot. It's an invariant, right? Should this be happening? Right, so then it gives you ideas about how to modify your properties, and that's I think that's the big value of this work. So some other sort of high-level thoughts on automating these steps. So step 5, I think that there's some good work that's being done here. There's actually a lot of work now, not surprisingly, using LLMs to do this kind of stuff. I'm a little skeptical on that, but maybe it'll work. Steps 1 through 5, I think for sure require a higher notion of specification. So this sort of property, I say, is pretty much akin to like an assembly language formal flow property, right? It's pretty low level, right? And I think if we want to make any progress on these, automating the rest of this, which we need to do in order to make our hardware more secure, we need better languages to model those properties, how we want to specify security behaviors or properties. So I'll talk about that more in a second. There's a lot of really great work, and I think Paul's probably familiar with a lot of this stuff on very specifically looking at ISA and looking at information flow and security properties on specific ISAs. So looking at the ISA and looking at the microarchitecture and saying, does this microarchitecture have any bad flows that we don't want? These Spectre meltdown plus stuff, right? And so there's a lot of great work there, but I think there needs to be more general work. I think that's a very specific thing. Obviously, that's something you would look at first. ISA is a really important sort of microarchitectural to architectural to microarchitectural type of thing, but we need to extend beyond that, right? And then there's a ton of ML stuff. Mark Taranopar's group and Farame Farandi at Florida are doing a lot of work on this space. They have a company on this stuff. It's hard, I think, just because there's not a lot of good, to my earlier point, there's not a lot of good examples of hardware designs in the wild. And so those LLM tools don't work too well because they don't have good examples of them. And there's even fewer examples of flaws on hardware designs in the wild because companies don't want you to know those, right? If they find them, right? And so basically the best ones are these hack-at competitions, hack-at DAC, hack-at, and Chess have one, hack-at Chess not yet, but anyway, hack-at CCS, whatever. And they put flaws in there. And then a lot of these machine learning tools now are saying, look, I can find all these flaws that are at these hack-at competitions. Of course you can. Of course you can, right? So this is, but I have been doubting I've been one of those people, machine learning is overhyped. And I've been saying that for 15 years, and I've been wrong for 15 years. So who knows? Who knows? Okay, so what I do believe is we need a common infrastructure for security verification, hardware security verification. So some things that are really simple, back to the first question, is like this code of influence thing. That's a simple thing that we should all be doing. But we maybe don't do that because we don't have a good compiler infrastructure to do that, right? Module hierarchy, mixing specification, information flow constraints, path conditions, reachable states, all these sort of things are things that all of these verification tools really need, but may not do because there's not a good framework for using this, for doing this, okay? If you look at a lot of really good research recently in the compiler space, in the hardware design space, you see that there's a lot of good intermediate representations, a lot of good basically compiler frameworks, right? So MLIR and Circuit is a sort of a compiler version for MLIR, and LLVM, started the whole sort of open source compiler stuff. And Yosis is an amazing tool, and Fertile, and gosh, I forget what this is, Slang. Really good frameworks, but none of them really think about security, unfortunately. So we've been starting to think about that. So how do you make a compiler verification or hardware security compiler, hardware security compiler that thinks about security? So well, obviously you need security as a first-class citizen. You need, it's pretty clear that information flow tracking is fundamental to security. So information flow tracking was done by Dorothy Denning in the 70s when she was at Purdue, right? This is a fund for operating systems. This is a fundamental security technique that has been shown time and again, operating systems, compilers, software, microarchitecture, architecture, hardware, that is important, right? So you need something like that. I think visualization helps, and I'll show you some visualizations. We need to not reinvent the wheel, stand on the shoulder of giants, and it needs to be scalable, right? So this is our attempt at this. This is R, is Andy. Andy's my amazing PhD student. So what Andy did is he took Slang. Slang is a really good open source system Verilog. Unfortunately, it doesn't support like VHDL, but it's like really industrial level. So we've run Slang on internal Intel designs and it works. So it's a really strong compiler, open source. So he took Slang and he's building on top of that. Maybe Yosis is Yosis isn't as good as a Slang if you look at sort of some of the benchmarks, but it's still good. Maybe that's another option, but we chose that. And so we use that, so standing on the shoulder of the Slang giants. And then we also take some information flow stuff. So this is Security tools, because that's what we have really good access to. But this could very much be Zurich, Zurich professor, forgetting his name. Anyway, FT is a really good open source sort of version of Security grading tools. It could be that, right? But what we do is we take this information flow tracking stuff and we annotate this Slang stuff with security features. And then we can do analysis based on that. Okay, so let me talk a little bit about this. So the flows that we care about are two that are static flows or structural flows, I would say. One is explicit flows. So B goes to D. B is assigned to D. C is assigned to D. It's explicit flow of information, right? C is assigned to D. B is assigned to D, right? And then you also have explicit flows. Implicit flows, sorry, I always mess those up. Implicit flows, explicit flows, direct. Implicit flows are usually timing flows in hardware. These are timing flows, right? So if this, then one of these happens. But basically, the time at which D is set is based on this condition, and it will change based on that condition. So for A, depending on what A is, it will tell you, D will get set at different times. So you care about those things, but they're a little bit different. So sometimes in your threat model, companies come to Security and they say, we care about these things, but we don't care about timing channels. Timing channels are just we don't care. Our customers don't care. We don't have time to worry about those, but we do care about these things. These are more important to us. So you want to separate those two things is my big point. You can take this. This is actually it looks like the Death Star kind of. But you can take that OpenTitan one-time programmable hardware module and compile it through Slang and visualize it. And then you can say, here's only the explicit edges, here's the implicit edges, and then here's that flow we saw earlier. And Andy made this really cool website. If you want to go, you can actually sort of move this around and look at the different signals and things like that for this example. So it's, I think, a nice example of showing how through a bunch of open source tools, all the way from hardware compiler tools to visualization tools, that you can get more insights about your design. You can also start thinking about different types of metrics. So that signal connectivity metric, that's the one we used for FastPath. Is it connected? Okay. And then there's a bunch of other metrics that you can do with test benches. So how many paths are activated with this test bench? How far away did the flow get from my a potential sink, a bad thing? How much information flow is there at a certain time? How much information flow has there been totally? How many bits? How many bits have changed, right? So you can start thinking about different metrics. And something that we just started thinking about that I think will probably either get done by someone else or maybe our group at some point, because there's a ton of work right now on hardware fuzzing, is using these sort of metrics, these flow metrics, to guide a fuzzer. So if anybody's interested in doing that, please talk to me, because I'd love to have. I think this is a really good idea. I just don't have the student right now. I have Andy, but Andy's a little oversubscribed. Andy will help, but Andy can build all this stuff. So this is that test bench. So there's 207 test benches in OpenTitan. And this is a bunch of outputs that we cared about. And then this is saying how much, what is basically the cumulative flow of all these sort of things. So if you look at these sort of, the intensity of this is saying for this test bench here, this output gets a lot of flow, right? So it's sort of indicating to you that this test bench is good. Like this test bench is kind of garbage for this property because it doesn't make any flow happen, right? But maybe this test bench, I don't know what that test bench is, but that is, and so it sort of guides you to say like, this is a good test bench and this is bad. And that's what you need for fuzzing, right? You basically need for fuzzing to say, is this a good thing or a bad thing, right? So I think that there's a really good opportunity to do this. Okay, so the last maybe somewhat major thing that I'll talk about is debugging, which I think gets over. So this is the property fails. The property almost always fails. Okay, that's job security, right? For Security, that's what keeps the lights on at Security, right? The company comes to us and says, "Is our design secure?" And we laugh and so we'll check it out. We'll check it out. We'll try to find a flaw for you, right? And then we run it. We're like, "Look at this thing we found, right? There's a potential flaw here, right?" Like, "Oh my gosh, really?" So most of the times it's not a big deal, but sometimes it is, right? But then you have to debug it. Then that's right. That's focus in that loop of like, is it my property issue or is it actually a bad flow, right? That's a really smart, soon-to-be PhD graduate, probably a professor if I had to guess, spending a month or 2 months on a design to think about whether is this a real issue or is this a specific property specification issue, right? And that's the pain. That's the pain point in verification right now. So this is kind of how it works. We write the HDL, we write the properties. Most often, these are separate teams. This is the team that just does processor design or crypto core design or whatever. They are the system Verilog people, okay? These are the security experts. They come in and they write these properties, right? And they fail. They always fail, okay? And then we're like, okay, we got to fix it, okay? And then the security experts are like, this is a hardware problem. You got to fix it, right? And the hardware designer is like, no, this is a security issue, right? You got to fix it, right? And that's really the pain because it takes a person. It either takes a person who knows both of these, which are probably some of you in this room, and you're very valuable, right? So you're worth a lot. And despite probably not getting paid a lot right now, you're worth a lot when you graduate. Or it takes these people teaching these people and vice versa to understand this problem. Okay, so that's the big challenge. All right, so how can we help this? We're gonna fix this, but how can we help this? So there's a bunch of things here. This is the iterative loop. So we start up here, OpenTitan design, hardware design, and we have our properties. So we start here and here, we do this verification thing, and it fails. So the failure means it's a problem. I should put another failure here, and it said, or it's a property refinement that I have to do. I rewrite my property isn't specified well, I come back, I run it again, and eventually maybe I find a failure, and then I have to figure out what I need to change, and then I have to change it. Okay, so localization and repair, and then I sort of do this whole process again and again. Many years back now, pre-COVID, Armida was my first COVID PhD defense. I remember that very specifically. Being online is like, oh, this is kind of crazy, and oh, this will only be a few months, and we'll be through with it, right? So she graduated right as COVID started, but she made this really amazing tool called VeriSketch, and this is the notion of sketching. So sketching is a software, largely a software thing. So a guy named Armando at MIT is very famous for this. So the idea with sketching is you take a design, take a piece of software, and then you sort of put holes or question marks in it. You say, I don't know exactly what this line of code should be, or I don't know exactly what this variable should be. And then you give it to a formal tool to solve it. It's a really powerful thing. So we took that and we did that in hardware. And we said, okay, can we take these security properties, and let's not worry about what this property is. This is related to a cache side channel. We take this cache side channel. This is one of Ruby Lee's cache side channel that was supposed to be resilient to this, but actually we found out wasn't. We say, is it secure? No. Well, man, Ruby and her students, they're a smart group of people. They wrote this thing, but actually it has a problem. We found the verification, we found a flow in this that shouldn't be there. It was actually a flow on metadata. So the tags were, it was very sort of meta, right? The tags were giving flows. The way that the tags were being set or not being set, or being evicted or not being evicted, were giving flows. How do we fix this? Well, I don't know, man. This is a hard thing, but it would be a lot easier if we could just sketch it. So we say, this skip signal is important, but I don't know exactly what it should be, but it should be a function of these signals. And this if condition is also important, but I don't know exactly what it should be, but it should be a function of these two signals, okay? Or, I kind of know it should be on a not hit and something, or I kind of know it lock should be equal to something, but I don't know exactly. Should it be 1 or should it be 0? Figure that out for me, right? And then the sketching will figure it out for you. It's somewhat magical. It's formal, and it doesn't, if you try to sketch everything, you say, I don't know anything, it'll say, I can't tell you anything about that. So you need to localize it fairly well. But it uses a lot of this sort of framework that's been built up in the software community for quite some time, solvers to be pretty smart about this. And so see, these are some of the sketching things, not super important, but basically you can say, I don't know certain things. And this is the language that we developed to say, I don't know this thing. Okay. So let me sort of, what did I do here? I ran out of time last night and I didn't fix my slides. So here's, let me summarize this, and maybe I'll have a couple minutes to do something real quick. Sort of in order of most importance, so top to bottom, what I think are most important. So this open source verification framework, I think that's really important. If we can make a big impact there, I think that's going to have a big impact on the community, academic community, the industry community. I think debugging, not a whole lot of people are thinking about debugging. I don't know why. Maybe because it's hard, but metrics are important. Maybe a lot of people are starting to think about that. Scalability is important. And then also automating steps 1 through 5, I think is fairly important. So let me skip. These are some of the things I do in my group, but I don't want to, let me just talk quick. So I do a bunch of stuff in my group. I know you're all security stuff, but I build a lot of systems with ecologists and biologists. So if you're interested in this kind of stuff, let me know. We build stuff for archaeologists and people studying mangroves and people studying fish and San Diego Zoo, oceanographers. It's a cool program. It's going on right now. It's I'm happy to be in Germany, but I'm kind of sad because I'm missing a lot of the work that's being done this summer by a bunch of great undergrads in this. We also do a lot of work with FPGAs. And I know a bunch of you do FPGA sort of security stuff, but we do a lot of FPGA design, so fast accelerators at the edge. A great example of that is the Large Hadron Collider. So we've been working with people at CERN and Fermilab, a bunch of physicists, really cool people, on developing things at what they call the extreme edge. So terabytes per second coming in, filtering stuff that we do on FPGAs. So a lot of sort of really fast, ends up being machine learning stuff at the edge. We have a cool project on, it's called junkyard computing, as we say, these phones that we have, that if you're anything like me, get rid of on average, an average American, I should say, maybe Germans are better. Average American gets rid of these phones every 1.5 to 2 years. Yeah, and 80% of the carbon cost of this phone is in the manufacturing of it. Okay, it's not in powering it, because it's pretty low power, right? So why do we get rid of it? We want a better camera so I can take cuter pictures of my daughter, right? The screen is cracked, right? Because I need a new screen. I need whatever, right? These different things. But it turns out the internals are still really useful. So we have a fairly sizable project funded mostly by Google and the U.S. National Science Foundation is how do we repurpose these phones? And it turns out we're making racks of these phones and putting them into data centers at Google and also at UCSD. I'm happy to talk about that kind of stuff. It's a whole talk that I don't have talked. And I promised this thing, but I have zero time for this. Maybe in a month I can give another lecture or something like that. But this is a really cool, I know you do a lot of side channel work here. A really interesting side channel that we found that's related to bias temperature instability. So it's a very analog side channel that has to do with how you're using the gate. And it has to do with, so the really cool thing about this is that, you all know power side channels, right? So with a power side channel, the thing has to be computing, right? And it gives us a power signature. The cool thing about this is that you can figure out things about how it was computing. So the way that it was computing will make this gate run faster or slower. And it's a thing called bias temperature instability. It's a thing that's really well known in semiconductors. It's a bad thing. They're fighting it all the time. But if you set this as a 1 or a 0, it's going to have a different delay. And so it turns out, you can see that. So here's this FPGA. We set a bunch of wires to 1 and 0. And then we burned it in for quite some time, so 200 hours in an oven. So this is very contrived, right? And then you can see it rebounds, and it behaves differently depending on whether it's a 1. And in fact, we did that on AWS, so on F1 instances. And we're able to see pretty well how to pull out keys. So that's a talk for another time, because that's a very deep thing. But also happy to talk about that anytime. Christoph said, I'm going to be here for another couple of months, so I'd love to talk to all of you. This is my research group. These are my collaborators. These who I want people to be my collaborators. Okay, so I want to add your name, all of you, your names to this, right? I'm serious. I think collaboration is super duper important, and that's how the best research happens. You guys have amazing, cool things going on here, and I think can do some good things. So that's all I have. Thank you.